A leopard chasing a deer. An aircraft chasing another. These tracking routes can be called pursuit curve. A pursuit curve is a mathematical curve that describes the path followed by one object as it pursues another object. Pursuit curve is shown as this animation. For example, red point assumed as leopard and black point assumed as a deer. With the path of pursuer and pursued parameterized in time, the pursuit is always on the pursuer tangent. Through pursuit curve, we can predict the time or position they collide. We can apply first-order ordinary differential equation to solve the pursuit curve problem. A first-order ordinary differential equation is the type of differential equation that involves only the first derivative of an unknown function and the function itself. It can be generally expressed in the form of dy over dx equal to function of x and y. These are the type of first-order ODE. In this video, we are going to solve the pursuit curve problem and model it into separable equation and solve it using separation of variable. A separable equation is a type of differential equation that can be written in the form of dy dx equals to fx times gy, allowing the variable x and y to be separate on opposite side of the equation. For example, integrate 1 over gy dy is equals to integrate fx dx. This form allows the equation to be integrated with respect to x and y independently. So this is how we can solve the separable equation. This process typically involves finding antiderivative which allow you to solve for y in terms of x.
Imagine a tense battlefield scenario. You are part of the military defense team and suddenly an enemy fighter jet enters the airspace of your country. The commanding general issues a direct order to shoot down the intruding aircraft. The responsibility now falls on the engineering team to ensure that the guided missile successfully intercepts the enemy jet. As an engineer, your task is to determine the exact path the missile should take to collide with the jet. So let's see how we can determine the curve of the missile trajectory by using the first order ordinary differential equation. First, let us rotate this scenario and represent it using a graph. Now, 3 things to note. First, we are going to assume that the fighter jet being chased has a predetermined path, which in this case it is traveling in a straight line. Then, the second assumption is that the missile is always moving in the direction pointing towards the fighter jet during pursuit. Besides, we have to assume the speed of the two objects is constant, which means no acceleration. But we still need more details to solve this problem. So let's assume that missile traveling at a speed w is pursuing fighter jet which is traveling at a speed v. In addition, assume that missile begins at the origin and pursues fighter jet, which begins at the point h, 0, and travels up the line x equal to h. After t hours, missile is located at a point p, xy, and the fighter jet is located at a point q, h, bt. The goal is to express the curved trajectory of missile, that is to find y as a function of x.
So now let's go to the problem solution. In order to solve this problem, we can find the first equation from the gradient of this curve. To find the gradient of this curve, a straight line is formed between point P and point Q. The gradient of the straight line is change of y over change of x, which is dy over dx is equals to bt minus y over h minus x. We aim to isolate t in this differential equation. After arranging, we will get t in terms of x, y, and y prime. For the second equation, we let L is equals to the distance traveled by the missile. As we know, speed of the missile is w, so we will get L equals to wt. Besides, we can also find the L by using the arc length equation. Therefore, a second equation is formed. Now we have equation 1 and equation 2. Then, by using the substitution method, we get this equation. After substitution, we differentiate both sides of the equation with respect to x, and we will get this equation. But then, our equation is second order differential equation, which is quite hard for us to solve. So, we can use substitution to convert it into first order differential equation, which is let y prime prime equals to dp over dx and y prime equals to p. Then the first order differential equation is formed. By solving this separable equation, we get this equation. At initial condition, t equals to 0, x equals to 0, and y equals to 0. And we got c equals to ln h. Then we substitute c back to the equation and simplify the equation to express p in terms of x. By using the definition of Shine, we simplify it into this form. After substituting p with dy over dx, a first order differential equation is formed. By solving the separable equation, we integrate both sides and use definite integrals for the right hand side from 0 to x. By setting the range, the shape of the curve can be changed according to the value of x. We will get this equation by solving the integration. After that, a general equation of pursuit curve is formed by further simplifying the equation. Now we have the general equation of pursuit curve. In order to find the point of collision, h, y, so we need to substitute the x equal to h and we will get this equation. To find the time of collision t is equals to the distance over speed. By substituting the previous equation of y, we can get this equation.
Next, we apply all the equations derived before the start in the real-life scenario. Assume that we had the following situation, which are the fighter jet with constant velocity 5,000 km per hour chased by the whistle with constant velocity 10,000 km per hour toward the direction of fighter jet in the pace of pursuit curve, and the altitude is set as 10 km. By using the derived formula, we found that in this situation, the point of the collision is 10 and 6.667 and the time of the collision is 4.8 seconds. Now, we stimulate this real-life situation by the aid of the GeoGebra. The image of the fighter jet and the missiles are shown. Now we run this graph. It is found that the coordinate of collisions are located as 10 and 6.667 with collision time 4.8 seconds, which are accurate with the theoretical value. Hence, by knowing the three values which are the velocity of two objects and the straight line distance between two objects, we can form a pursuit curve with variation pattern by using the general equation.
All in all, we can conclude that the separable equations in the first order ODE can be widely used in many types of problems, especially in real-life scenario. For example, Newton's law of cooling, population growth, and also radioactive decay. We also proved that the problems regarding pursuit curve can also be solved as separable equations. The general equations that have been discussed in the previous example is relevant only when the target is traveled in a straight line. However, the way of travel can be different, for example, in the circular motions and etc. Besides, there are different types of pursuit, such as pure pursuit, lead pursuit, and also lag pursuit. Therefore, we can say that the curve for pursuit can be applied in various fields, such as military tactics, prey and predator dynamics, robotics, astronomy, and also game development. That's all for our group video presentation. Thank you for listening and we hope that this video may help you out. If you are interested in exploring more about the pursuit curve, just click on the link provided in the description box below. All the references as well as the graph animation link that have been used in this video are attached in the description box. Hope you enjoy it. Thank you. Last but not least, this video is presented and credited to members of Group 2 from SSCE1793 Section 34.